By 1942, quartermaster records from 3 separate theaters told the same story. Soldiers were building their own weapons, not improvising, not adapting. Building from scavenged metal, stripped enemy equipment, salvaged vehicle parts, and whatever the ground around them happened to offer. The supply chain had a term for the gap between what a unit was supposed to have and what it actually had in the field. They called it the deficit. The soldiers had a different term. They called it Tuesday, because the trucks didn't always come. The airdrops landed in the wrong coordinates. The resupply convoy hit a mine 3 kilometers back, and everything on it, ammunition, rations, replacement parts, became someone else's problem. And the fight didn't pause for paperwork, so they built, with hands that hadn't been trained for fabrication, with tools that weren't designed for weapons manufacture, with the particular ingenuity of men who understood that the alternative to a working weapon was not a regulation, it was a grave. These are the 10 improvised weapons WW2 soldiers built when the supply lines failed, and the stories of the men inventive enough, desperate enough, and determined enough to build them. Number 10. The bootleg Bangalore torpedo. The demolition tool soldiers built because command wouldn't send enough. The standard Bangalore torpedo was not a complicated device, a metal pipe, an explosive charge, a firing mechanism, pushed along the deuce upright, ground beneath wire obstacles, detonated, and the wire along with anything immediately adjacent to it ceased to be an obstacle. The British Army had been using variations of the design since 1912. By World War II, it was standard engineer equipment, officially manufactured, officially issued, officially present on every equipment. Manifest for units conducting assault operations against fortified position, officially. The reality in the field, particularly in the Pacific Theater and in the hedgerow country of Normandy, was that official quantities were never enough. An assault on a fortified beach position might require a dozen Bangalores to clear multiple wire belts across a 2 to 100-meter front. A unit might be issued 4. The math didn't work. So engineers and infantry soldiers working in forward positions with whatever materials were accessible began constructing their own. Sections of salvaged pipe from destroyed vehicles and farmhouses, explosive fillers sourced from dud enemy shells, carefully and extremely dangerously extracted and repacked. Firing mechanisms cannibalized from damaged issued equipment. The results were unpredictable. That is the charitable description. A homemade Bangalore built from corroded pipe and improperly packed explosive filler was as likely to detonate prematurely as it was to clear wire. Engineers who built them knew this. They built them anyway, because a wire obstacle that couldn't be cleared wasn't a tactical problem. It was a killing ground. Combat engineers from the 1st Infantry Division, the Big Red One, were documented constructing field-fabricated Bangalores during the Plains hedgerow fighting in Normandy in July 1944. Their after-action report noted the improvised devices with the particular bureaucratic restraint of men who understood that what they were describing was simultaneously necessary and almost certainly against regulations. The report recommended that standard Bangalore allocation be reviewed. The allocation was not reviewed until 1945. The engineers kept building their own. Number 9. The Molotov cocktail Allied version. The weapon every army claimed they never used. The Molotov cocktail has a complicated provenance. The name itself was Finnish, a sardonic reference to Soviet Foreign Minister Vyacheslav Molotov, who had claimed during the Winter War of 1939 that Soviet aircraft dropping bombs on Finnish cities were actually delivering humanitarian food packages. Finnish soldiers, receiving the bombs, began calling them Molotov bread baskets. The incendiary bottles they threw back at Soviet tanks they called Molotov cocktails, a drink to go with the food. The concept was older than the name. Incendiary bottles had been used in the Spanish Civil War. They were simple, manufacturable from materials available in any occupied town, and effective against the specific vulnerability of early and mid-war tank designs, the engine compartment, the vision ports, the gap between turret and hull where flame could find its way inside. Every major army in WW2 officially discouraged their frontline infantry from using them. The reasoning was straightforward. A soldier carrying a glass bottle of flammable liquid in a combat environment was a soldier carrying a significant risk to himself and the men around him. Every major army in WW2 had soldiers who used them anyway. American infantry in the Pacific, specifically Marines fighting in the fortified cave networks of Peleliu and Iwo Jima, developed a particular application that the official record is careful not to describe in detail. Japanese defensive positions built into volcanic rock and coral were resistant to direct fire and BDs, difficult to approach with flamethrowers in certain configurations. A bottle of aviation gasoline accessible on every island with an airstrip with a cloth wick and a reliable ignition source solved a specific class of problem that the issued equipment sometimes couldn't. The 1st Marine Division's records from Peleliu in September 1944 do not mention Molotov cocktails by name. They mention improvised incendiary devices in 3 separate after-action summaries, each time with the notation that the practice was not sanctioned and that issued flamethrower equipment remained the preferred method. Preferred. Not required. Not always available. The bottles kept appearing. Would you trust the weapon the supply chain sent, or the one you built from what the ground offered? Number 8. The parachute silk silencer. The improvised suppressor that worked well enough to matter. Suppressors. The correct term for what popular culture calls silencers were not standard issue for any conventional Allied brider infantry unit in WW2. They existed. The Welrod pistol built one into its design. OSS operatives received suppressed weapons through specific procurement channels. For everyone else, there was nothing, which presented a problem in specific tactical situations. Reconnaissance patrols operating deep behind enemy lines, where a single unsuppressed shot could compromise a mission that had taken weeks to plan. Forward observers who needed to eliminate a specific threat without triggering a broader response. Night raiders who had identified a sentry and needed the elimination to be, if not silent, then at least quiet enough that the next sentry didn't hear it. The solution that appeared independently in multiple theaters among soldiers who had never communicated with each other was fabric. Specifically, the nylon and silk material from damaged or surplus parachutes, wrapped in multiple tight layers around a weapon's muzzle and secured with wire or cord. The material absorbed a portion of the expanding gas from a fired round, reducing the report to something that in field conditions, at distance, could be mistaken for something other than a gunshot. It was not effective by any technical standard. It degraded after a small number of shots. It affected accuracy. It was a field expedient in the most literal sense, a compromise, solution to a problem for which no issued solution existed. British paratroopers from the 6th Airborne Division, operating in Normandy in June 1944, were among the units documented using fabric-wrapped muzzle devices during deep reconnaissance operations. The technique appeared independently among OSS teams in Burma and among Australian independent companies operating in AG's Crete. New Guinea, the same improvised solution arrived at by different men in different jungles on opposite sides of the world. Necessity arriving at the same answer. Every time. Number 7. The biscuit tin anti-personnel mine. The weapon built from rations, buried in the dark. Mines were not improvised weapons in any conventional sense. The major powers of WW2 had invested heavily in purpose-built anti-personnel and anti-vehicle mine technology. The German S-mine, the Bouncing Betty in Allied soldier slang, was a marvel of industrial lethality. The American M1, A1 pressure mine was standardized, mass-produced, and present in quartermaster inventories across every theater. Present. Not always available. Not always in the quantities a unit needed when it needed them. The problem appeared with particular urgency in the Western Desert, North Africa, 1941 through 1943, where the Long-Range Desert Group and the SAS were conducting deep penetration raids against Axis airfields, supply dumps, and communications infrastructure across hundreds of kilometers of terrain that no supply chain could reliably service. You could not call for resupply in the deep desert. You carried what you had. You built what you needed. The biscuit tin mine was exactly what its name suggested, a standard British Army ration tin, emptied of its contents, packed with whatever explosive material was accessible. Captured Italian or German demolition charges were preferred, fitted with a pressure-sensitive firing mechanism cannibalized from damaged issued mines, or constructed from bent metal and prior, spring material, and buried at a depth and angle calculated to detonate under the weight of a vehicle wheel or a human foot. David Sterling's SAS, operating from forward desert bases that received resupply by air when weather and enemy activity permitted, and by nothing when they didn't, documented the construction and deployment of biscuit tin mines in unit. Records from the Libyan operations of 1942. The mines were crude, their reliability was inconsistent. A professionally manufactured mine had quality control, standardized explosive fill, tested firing mechanisms. A biscuit tin had none of those things. What it had was availability. It existed wherever British soldiers ate rations, which was everywhere British soldiers operated. In the logistics calculus of the deep desert raid, a weapon that could be manufactured from materials already present in the unit's kit was worth more than a superior weapon that was 300 kilometers away on a truck that hadn't arrived. The SAS buried them along withdrawal routes, along approach roads to targets they had just hit, at water points that Axis forces would need to use within the next 24 hours. Crude, inconsistent, exactly sufficient. That was the standard the desert set. Number 6. The molten lead grenade. What Pacific soldiers built when the crates ran empty? Grenades had a logistics problem that no quartermaster could fully solve. They were heavy, they were bulky, they were consumed at rates that supply chain planners consistently underestimated because supply chain planners were working from doctrine, and doctrine had been written for a war that looked different from the one being fought. In the Pacific, the grenade consumption rate during island clearing operations moving through fortified cave systems, bunker networks, and tunnel complexes exceeded projected rates by margins that unit supply officers described in after-action reports with a specific kind of bureaucratic exhaustion that reads, decades later, as barely contained fury. They were asking for more grenades. The grenades were not coming, not in time, not in the quantities needed. So soldiers improvised. The specific improvisation varied by theater, by unit, by what materials were locally available. In the Pacific, one solution that appeared among Marine and Army units on multiple islands involved the casting of improvised fragmentation devices from whatever metal could be melted. Down lead from vehicle batteries, brass from spent casings, aluminum from damaged aircraft components, poured into improvised molds constructed from salvaged materials, fitted with firing mechanisms stripped from dud enemy grenades, or constructed from locally available materials. The results were heavy, irregular in shape, unpredictable in fragmentation pattern. They were also grenades, at a moment when the issued grenades were gone and the next supply drop was 48 hours away, and the position needed to be taken now. An imperfect grenade was not a compromise. It was the difference. A supply officer with the 7th Infantry Division, the Light Hourglass Division, operating on Leyte in the Philippines, in late 1944, documented the practice in a report that recommended immediate review of grenade allocation. Formulas for jungle clearing operations. The allocation formulas were reviewed. The soldiers kept building grenades while they waited for the review to conclude. If you've made it this far, you understand this is not about heroes or villains. It's about choices made under pressure. Stay with me. The improvised grenade represented something that the supply chain's architects had not fully modeled: the human capacity to look at an empty crate and decide that the emptiness was a problem to be solved rather than a condition to be reported. You could file a requisition form, or you could find a battery and a mold. The form took 3 days to process. The grenade took 3 hours. In the jungle, in 1944, 3 days was a different kind of number than it sounds. Number 5. The Sten gun copy. The weapon so simple, occupied Europe built it in bicycle shops. The Sten gun was not a beautiful weapon. British soldiers who received it in 1941 were not impressed. Crude stamped metal construction. A magazine that fed from the side at an angle that made prone firing awkward. A safety mechanism that experienced soldiers trusted approximately as far as they could throw the weapon itself. A tendency documented, complained about, never fully resolved to praisen. Discharge if dropped on a hard surface at the wrong angle. It was also cheap, extraordinarily, deliberately cheap, approximately $5.30 in 1941 currency, to manufacture. Simple enough that a competent machinist with basic equipment could produce a functional copy without access to specialized tooling or materials. That last characteristic was not an accident. It was doctrine. The SOE had looked at the Sten's design with a specific strategic purpose. If a weapon could be manufactured in a bicycle repair shop, it could be manufactured in occupied France, in occupied Denmark, in occupied Poland, in every country where resistance networks needed weapons and Allied supply drops were insufficient, unreliable, or both. They were right. Sten copies appeared across occupied Europe in quantities that the German security apparatus found genuinely alarming. Danish resistance workshops produced functional Sten copies from salvaged materials throughout 1943 and 1944. French maquis cells in the Dordogne and the Haute-Savoie were Tessidam manufacturing copies from steel tubing and scavenged parts, while simultaneously receiving official SOE supply drops that never quite covered the gap between what they had and what they needed. The copies were not identical to the issued weapon. They were sometimes cruder in finish, sometimes tighter in tolerance, occasionally in the hands of a genuinely skilled machinist working from memory or from a captured example functionally superior to the original in specific characteristics. A resistance armorer in Lyon, documented in SOE Field, reports from late 1943 had produced 43 functional Sten copies using equipment that included a metal lathe, salvaged from a bombed factory, hand tools and steel, tubing originally intended for plumbing installation. 43 weapons from plumbing supplies. In an occupied city, under German administration, the armorer was 26 years old. When SOE officers examining the copies asked how long each weapon took to produce, he said approximately 14 hours per unit, working alone, working at night, with the windows covered and the door locked, and one ear always on the street outside. 14 hours. 43 weapons. 602 hours of work done in the dark, in silence, with the knowledge that discovery meant something that the word consequences fails to adequately describe. That is a different kind of courage than the one the history books photograph. Number 4. The welded shotgun Australian Owen predecessor. The backyard weapon that became a military contract. In 1939, a 22-year-old Australian named Evelyn Owen was working at a steelworks in Wollongong, New South Wales. He was not a trained engineer. He was not a weapons designer. He was a young man with mechanical aptitude, access to basic metalworking equipment, and an idea about submachine gun design that he could not stop thinking about. He built a prototype in his parents' backyard. The Australian Army rejected it. They were interested in the Sten, in the Thompson, in weapons that came with established manufacturing infrastructure and allied standardization credentials. A backyard prototype from a steelworks employee in Wollongong was not what the procurement office was looking for in 1939. Owen joined the Army. He took his prototype with him, unofficially, unauthorized, stuffed into his kit with the particular stubbornness of a man who believed in what he had built, even when the institution responsible for evaluating it did not. He kept showing it to people. A lieutenant colonel named Clive Caldwell, not his commanding officer. Not anyone with direct procurement authority saw the weapon, understood what he was looking at, and escalated it through channels that Owen had not been able to access. By 1941, the Australian Army was testing the Owen submachine gun in formal trials against the Sten and the Thompson. It outperformed both in the tense conditions that mattered most for Pacific jungle. Warfare reliability in mud, reliability in water, reliability in the particular filth of the environments where Australian soldiers were going to fight. By 1942, it was in production. By 1943, it was in the hands of Australian infantry across New Guinea, the Solomons, and the island campaigns that would define the Pacific War's southern arc. 145,000 units produced. From a backyard in Wollongong, from a prototype that the Army had already rejected, carried unauthorized through basic training by a young man who could not accept that the institution's first answer was the final answer. Let that sink in. The Owen gun was not improvised in the field, but it began as something the system had refused, a weapon that existed only because one person decided that rejection was a starting point, not a conclusion. Sometimes the most important improvisation is not the one you make under fire. It is the one you make before anyone is shooting, when the only thing pushing you forward is the certainty that you are right and the institution is wrong. And the difference between those two positions is going to matter when the shooting starts. Owen was right 145,000 times over. Number 3. The beehive directional charge. The explosive device soldiers engineered from enemy munitions. Shaped charges, explosives configured to focus their blast energy in a specific direction rather than dispersing it uniformly were not new technology in WW2. The Monroe effect, the underlying physics of focused explosive energy, had been documented since the 1880s. Military engineers understood it. Specialized demolition units had access to purpose-built shaped charges for specific tasks, cutting through vault doors, breaching reinforced concrete, defeating hardened steel obstacles. What they did not have was a shaped charge small enough, light enough, and manufacturable enough in the field to address the specific problem that kept appearing in the Pacific and in the Italian campaign: the Roken 7 reinforced bunker, the hardened firing position built from concrete and steel and packed earth that direct fire couldn't silence, and that a frontal assault approached at catastrophic cost. The solution that emerged, documented independently among combat engineers in multiple theaters, involved the careful disassembly of captured enemy munitions, Japanese artillery shells, German anti-tank rounds, Italian demolition charges. All of them contained explosive compounds that, properly extracted and reconfigured, could be shaped into directional charges using copper plate salvaged from vehicle components, electrical wire cannibalized from damaged communications equipment, and firing mechanisms stripped from dud rounds. The resulting devices were called beehive charges. In some unit records a reference to their roughly conical shape, wide at the base and narrowing, to the point where the focused blast would exit, placed against a bunker aperture, detonated remotely, They converted the energy of captured enemy explosive into a focused, penetrating force that the reinforced position had not been designed to resist from the inside. Combat engineers from the 5th Engineer Battalion, supporting the 5th Infantry Division during the drive through the Siegfried Line in late 1944, documented the construction of field-fabricated directional charges in a technical report that their commanding officer forwarded to Army engineers with a recommendation that a standardized field, manufacturable version be developed for issue. The standardized version reached units in 1945. The engineers had been building their own since 1943. 2 years of field fabrication, 2 years of working with captured enemy explosive in forward positions, under conditions that made every step of the process a calculated risk. They built them because the alternative, the frontal assault against a position that issued equipment couldn't silence, had a body count that the engineers had seen and refused to accept as inevitable. Crude, dangerous to construct, precisely effective in the moment that mattered. That was the calculation. Every time. Number 2. The Molotov breadbasket cluster, the improvised area weapon that air crews built in the dark. Strategic bombing in WW2 operated on a scale of industrial planks graded WW precision that its architects described in terms of targeting doctrine, bomb pattern analysis, and circular error, probable the statistical language of aerial warfare that transformed the act of dropping explosives on human infrastructure into something that could be discussed in conference rooms with charts and slide rules. The aircrews doing the actual dropping had a different perspective. A B-17 crew flying a mission over industrial Germany in 1943 was not thinking about circular error probable. They were thinking about flak, about fighters, about the specific and immediate mathematics of getting the aircraft and the men inside it back to England in one piece. And they were thinking about the bomb load because the bomb load was the reason for everything else, and the bomb load was not always what the mission required. Standard high explosive bombs were designed for specific target categories, industrial facilities, transportation infrastructure, hardened military installations, against area targets, supply dumps, vehicle concentrations, troop assembly areas. They were less efficient than incendiary weapons that could spread fire across a wider footprint. Incendiary weapons were not always available in the beat quantities needed. The bomb bay had what the bomb bay had, and the target was what the target was. The improvisation that appeared among British RAF bomber command crews and, to a lesser degree, among USAAF crews operating from English bases, involved the reconfiguration of available ordnance into improvised cluster arrangements. Standard incendiary sticks the 30-pound AN M47 or the British 4-pound incendiary, bundled in groups using wire, cord, or salvaged metal banding stripped from equipment crates, arranged in the bomb bay, in configurations that would separate on release and cover a broader area than single weapons dropped in sequence. Ground crews, who performed these modifications, were working without formal engineering authorization. The reconfigurations were not in any bomb-loading manual. They were developed empirically. Crews noticed that certain improvised arrangements produced better results against certain target types, documented the observation informally, shared it with other crews through the particular word-of-mouth network that forms among people doing dangerous work together. A ground crew chief with the 91st Bombardment Group, the Ragged Irregulars, operating from Bassingbourn in Cambridgeshire, described the process in a plain post-war interview with characteristic understatement. We figured out what worked. Then we did what worked. 8 words. The complete philosophy of field improvisation applied at 30,000 feet. These weapons were not built by accident. They were built by choice. And the closer we get to number 1, the higher the stakes become. The improvised cluster represented something that no targeting doctrine could fully model the intelligence of the man closest to the problem. Not the planner, not the procurement officer, not the engineer at the drawing board in a facility 3,000 miles from the nearest flak burst. The crew chief, the bombardier, the person whose hands were on the equipment and whose life depended on the equipment working. They knew things the manual didn't. They built what the manual hadn't thought of yet. And somewhere over occupied Europe in the dark, at altitude, with the target coming up fast, it worked. Number 1, the jerrycan, the container that won the war, and that high command spent 3 years refusing to copy. This is not a weapon, not in the conventional sense. It fires nothing. It cuts nothing. It does not appear on any equipment manifest, under the category of arms, or ordnance, or combat equipment. It is a fuel container, and it won the war in the Western Desert more decisively than any weapon on this list, because without it, the weapons had nothing to move them, nothing to fuel them, nothing to carry them to the place where they needed to be. Here is the story that the histories of armored warfare consistently understate. In 1939, German military engineers solved a problem that every army in the world had been living with since the introduction of motorized warfare, the WW2 problem of fuel containment and transfer in the field. The standard Allied fuel container of the period was a thin-walled rectangular tin, crimped at the seams, fitted with a screw cap that required a separate tool to open, and prone to leaking at the seams under the thermal expansion and contraction of field conditions. It spilled, it corroded, it failed at exactly the moments when fuel was most critical and least replaceable. The German solution was the Einheitskanister, what Allied soldiers would come to call the jerrycan. 20 liters. Welded seams, not crimped. A triple handle. Design that allowed a single soldier to carry 2 cans simultaneously, or to pass a full can hand-to-hand down a supply line without setting it down. An air-breathing valve that prevented the pressure buildup that caused inferior containers to bulge and fail. A spout design that allowed direct transfer without funnels or additional planes. Equipment. It was, in the language of engineering, an elegant solution. Allied forces encountered it in North Africa in 1940 and 1941. They recognized immediately what they were looking at. British and American officers sent captured examples back through intelligence channels with reports that were unambiguous. The German container was categorically superior to anything in Allied inventory and should be reverse-engineered and produced immediately. The reports were received. They were reviewed. They were filed. Allied procurement bureaucracy spent the better part of 2 years explaining why immediate adoption was problematic, not as straightforward as field commanders were, suggesting retooling manufacturing lines, material, specifications, standardization with existing equipment, the 1,000 frictions of institutional change applied to a 20-liter fuel container while men in the pleasant Western Desert were losing tanks and vehicles and momentum because their fuel tins were leaking into the sand. Soldiers did not wait for procurement to conclude. From the earliest North African engagements, Allied soldiers were collecting, hoarding, trading, and fighting over captured jerrycans with an intensity that their commanding officers found simultaneously understandable and impossible to manage. A jerrycan taken from a destroyed German supply vehicle was worth more than its weight in almost any other commodity available in the desert. British 8th Army. Soldiers developed informal exchange rates. Jerrycans traded for rations, for ammunition, for favors, for the particular currency of men who understood that the object in their hands was the difference between a vehicle that moved and a vehicle that didn't. Field workshops began fabricating copies. Not precise copies, the tooling for welded seam. Construction wasn't available in forward positions, but approximations. reinforced versions of existing tins, modified containers built from salvaged materials that addressed imperfectly the specific failure points of the issued equipment. They were worse than the German original. They were better than nothing. They were built because the supply chain had been given the answer 2 years earlier and had not yet finished deciding whether to use it. General George Patton, characteristically direct in his assessment of logistical failures, described the jerrycan situation in the European theater in terms that his staff edited heavily before the remarks entered the official record. The unedited version, preserved in personal correspondence, made clear that Patton considered the delay in adopting the jerrycan to be one of the more consequential institutional failures of the Allied war effort, not because of the container itself, but because of what the container represented. The enemy had looked at a problem, solved it, and the institution responsible for equipping Allied soldiers had spent 2 years explaining why the solution was complicated. The soldiers on the ground had spent those same 2 years building workarounds, hoarding enemy equipment, and carrying the weight of a bureaucratic failure in their hands every time they moved fuel from one place to another. The jerrycan sits at number 1 on this list, not because it is the most dramatic improvisation, not because it involved the greatest danger to the men who built or used it. It sits at number 1 because it is the clearest possible illustration of the central truth this entire list has been building toward. The soldier in the field always knows something the institution doesn't. Not because the soldier is smarter, not because the institution is corrupt or incompetent, but because the soldier is standing in the specific place where the problem is real, where the retake consequence of the wrong answer is not a memo, and not a delayed procurement review, and not a budget line that needs reallocation. The consequence is the vehicle that stops moving, the mission that doesn't complete, the men who don't come back. The jerrycan was not improvised in the dramatic sense. No soldier welded one together under fire in the dark. But it was improvised in the truest sense. Soldiers looked at what the institution gave them, looked at what the ground required, and chose the enemy's solution over their own armies. Official answer. Because the ground doesn't care about procurement timelines. The ground only cares what works. Heavy. Simple. 20 liters of the difference between moving and stopped, between the mission and the failure, between the war the institution planned and the one the soldiers actually fought. That was enough. That was always enough. Here is what 10 items on this list have in common. None of them were built because the soldiers who built them were reckless. None of them were built because the men involved had contempt for the institution they served or the officers who commanded them. They were built because the gap between what the gap system provided and what the ground required was real, measurable, sometimes fatal, and the men standing in that gap made a choice, not a dramatic choice, not a choice that announced itself with certainty or confidence or the clean moral clarity that retrospect provides, a quiet choice, made in a forward position, in bad light, with inadequate materials and incomplete information, and the full knowledge that the alternative to building something was accepting a situation that was not acceptable. So they built a resistance armorer in Lyon working 14 hours in the dark, a combat engineer on the Siegfried Line extracting explosive from captured munitions, with Fadi-Desh, hands that understood the margin for error was zero. A ground crew chief at Bassingbourn reconfiguring bomb loads by hand in the English dark before a mission that might not come back. A soldier in the western desert holding a German fuel container, simple, welded, perfect, and understanding with complete clarity that the Schent institution he served had been given this answer and had not yet finished deciding whether to use it. They did not wait. That is the thread running through every item on this list. Not genius, not recklessness, not the cinematic heroism of men who knew they were making history, just the refusal to accept the gap, the insistence that between what exists and what is needed, There is always something that can be built with what is available, with what the ground offers, with what the hands know how to do even when the manual says it cannot be done. That refusal did not begin in 1939. It did not end in 1945. It is the oldest human response to the oldest human problem, the moment when the tool you need does not exist, and the moment cannot wait. You build. If that instinct interests you, if you want to keep going deeper into the history of the Krobliks, men who looked at impossible situations and built their way through them, then you already know what to do. This channel exists for one kind of person, the kind who looks at what everyone else accepts as fixed and starts looking for materials. Next time we go inside the programs that weren't improvised at all. The weapons that governments built in absolute secrecy, deployed without acknowledgement, and then spent decades insisting had never existed. Not field improvisation, something colder, more deliberate, and far harder to explain away. Stay with us.